Today I'll be talking about large blue tilted isocurvatures. This work was done while I was a graduate student at Wisconsin Madison and working with my advisor, Daniel Chung. Presently, as Gaurav mentioned, I'm right now at Indiana University as a postdoctoral fellow. This eerily seems like a Sai, but it's the logo of IU, and I hope it's clear I and you. Right, so what are we talking about? So I'm going to talk about an axionic theory. I'll try to explain what exactly is large blue tilted here, which pertains essentially to the power spectrum. So what exactly is a power spectrum and what is a hello? Yeah, what is a isocurvature in that sense? So this is essentially going to be a theory that has a k-square power spectrum. We'll see what k-square here implies or means. It's going to be one which has a strong interacting. Okay, so this way, it's just a bit tight. That's fine. Okay, is this clear? Yeah, but yeah. Um, Right. So as I was saying, this is going to be a theory which has an interacting background, and we'll see why, and also the consequences of that. And also it has a eigenmode which resembles a relativistic perfect fluid. This is in analogy with what we see in the CMB. So we have the photons and the baryons mixing together, and there's a nice sound speed that we get, and you get exactly something similar. So this really resembles that situation. So as I said, I'll be talking about isocurvature perturbations. I'll introduce what these are. We'll talk about what are the current constraints on them. We'll look at the axionic model, so the Peccei-Quinn model, in fact, models. So the first part would be the most generic model, and second is how I can get new isocurvatures from a very generic model, but try to give it a bit twist. That essentially is going to be a rotating axion model, and we'll discuss the quantization and conformal phases for that. So let's begin isocurvature perturbations. So the isocurvature, so while talking about perturbations as such, there is something which we already all know and see, and that is the inhomogeneity in the matter density that we observe in the form of galaxies and stars. So that's just the inhomogeneity in sky for the matter. Apart from that, we also have measurements of cosmic microwave background, which is just the photons that we receive today. So they have a constant temperature today, background temperature of 2.7 kelvins. But then just like any other fluid, it has small fluctuations. The fluctuations in CMB are very, very tiny. They haven't grown since the time that they were emitted. So like 10⁻⁵, extremely small fluctuations. But the fluctuations in matter are interestingly have actually viralized, and they have grown to such an extent that what we see today in terms of galaxy and stars. So this picture actually gives you an idea. This is what we see. We see both of these today, but this still imprints a large amount of information from the time it was emitted. And this is about what has grown into what we see today. Right. So although we see these inhomogeneities, how do I explain? So we have radiation and matter, two fluids, and they are homogeneous in space-time. And there were some fluctuations which initially were there, and those fluctuations grew into what we see today. But how were these fluctuations seeded? And the most successful theory we have is that these were seeded by some primordial fluctuations. And I'll talk about where these primordial fluctuations come from, but what's important for us right now is to know that one can characterize these fluctuations as being two categories. So these are adiabatic fluctuations and the isocurvature fluctuation. And the way we distinguish between them is that if I have n number of fluids, so let's say I have baryons, I have dark matter, and I have radiation and neutrinos. If all of them can be defined, if all the fluctuations in them, so each fluid will have its own fluctuations, and if there is a common solution or a common eigenmode for them, mathematically speaking, if there is a common eigenmode or a common solution which defines the fluctuation for any number of fluids, that becomes an adiabatic. And if there is a common solution for any number of fluid, it means that common solution must have a very common origin. And we will see that inflationary physics actually explains it very well. But apart from the common solution, there is no reason why you cannot have differences between the fluctuations. And so the differences between them essentially becomes what we call isocurvature. So if there are n number of fluids, there will be n-1 relative differences between, let's say, fluid A and B. So I say A minus B, that kind of fluctuations. And there will be one common solution and n minus one isocurvature solutions. Here, I'm only going to talk about photon and matter, in fact, cold dark matter. So we are going to have just one isocurvature quantity, and that's going to be matter radiation isocurvature quantity. Any questions? And please feel free to interrupt me anytime. So this is, suppose I have the energy density, and I can have small fluctuations in the energy density of the photons and the baryons in an expanding space-time. So expanding, so we have, so suppose I have, even for a normal, so if I have this normal value of some amplitude for a uniform value of the energy density, I can have small quantum fluctuations. And these eventually will grow into what we see today, especially in the matter, but in photons, they remain exactly the same. And so it's this fluctuation that we are going to discuss. And these fluctuations originated during inflation, saying that inflation is the best theory we have as of now for primordial fluctuations. And so the idea is during the time of inflation, where inflation, let's look at this picture. So we all know about the Big Bang that gets said a lot in the popular sciences. And inflation is actually the time where the universe undergoes an accelerated expansion. And the expansion of the universe during inflation is something exponential. So some time and some large constant, which is extremely large, it's called the Hubble constant. And this is the time. So in a very small amount of time, let's say about minus 35 seconds, the universe actually expands a lot to what we see today, this size. I mean, this one, and then from there, it goes through different eras. There is an era where radiation is most important, and then there is an era where matter is more important. We are almost in an era where dark energy is more important right now. So these fluctuations are assumed to have originated during inflation. And as the universe expands, these fluctuations, these quantum fluctuations get actually stretched to what we see as classical fluctuations today. We are right now studying classical fluctuation, and then we map them back to study what were the quantum fluctuations back then. And that's how we get some idea about inflation and also the energy scale of the inflation. We are seeing dark. So assuming that we have different fluids, the idea is we have radiation, so I'll say a gamma, and then we have the baryons and the cold dark matter. And then we also have a fluid which currently drives the expansion of the universe, and that we say is the dark energy. So some dark energy fluid. And so the idea is that initially the universe was dominated by radiation, then eventually it got dominated by the matter, which is baryons plus cerium. And today, almost very, very recently, it got dominated by raw dark energy. And how do we know that? Because a dark energy would actually cause an expansion of the universe. And that's what we see today. Yes, exactly. Sorry, accelerated expansion, right? Thanks. Energy density of that particular species. Yeah, right. So if I were to probably make a plot to explain this better, no, it's not a conversion. It's actually how the different fluids, because the universe is expanding, so the energy density is reducing because the volume is continuously expanding, and how different fluids undergo this dilution. So if this is the total energy density rho, then the energy density of radiation reduces as inverse fourth power of scale factor. Scale factor here is just it's a dimensionless quantity which helps us know how is the universe expanding. It's like a scaling factor. So in a given period of time, has the universe expanded by twice or thrice, something like that. So in the radiation case, it reduces by gamma 1/4, and matter only goes as 1/a cube, and the dark energy is almost a constant. So that's somewhere here. So we see in this region, the radiation was most important. In this region, that matter was most important. And somewhere here right now, the dark energy is more important. And then knowing what we have today, we scale things back, and then we try to figure out at what point in time did all of these things happen. And then, of course, we have the point where inflation is somewhere here, and we assume that the fluctuations originated here, they got expanded during the inflation time, and then eventually they led to what we see today. Right, so today the age of the universe is about 14 billion years. So that's here. And this would be at about 73,700, about 300 years, right, roughly. And this is fairly recent, I would say about 4 to 5 billion years. That's where, or 10 billion years, I guess. That's where it began. Mm-hmm. Yes. Time is then defined in terms of today's time. So everything in terms of seconds and year in terms of how we measure it today. Right? Uh, okay, in order to give a more uh-huh. It's different. So yeah, that changes differently, and so the A increases differently in different parts of the. In radiation dominated, it increases differently compared to matter dominated. Almost all of the fluctuations that we see today for the matter started clumping together during this era, during matter dominated. And radiation did not really clump together because it was all these fluctuations on the radiation CMB came about only fairly recently, and by that time matter dominated had begun. So radiation did not really get any time to clump together or increase in size. But that's good for us because we have CMB that allows us to see very far back in time, and which gives us some idea of what those fluctuations were. And we have matter today, and we also know how much clumping had occurred. And using these, we can get an idea of how far back we are seeing. So let's take a look at inflation. So I'm assuming phi is a field which is causing the inflation here. And because this field causes an accelerated expansion, this is the field which dominates during that time. And any fluctuations or quantum fluctuation in this field would eventually also cause fluctuations in the energy density. So the energy density during inflation is given by this field, and fluctuations in this would cause fluctuations in the energy density. And because we are essentially looking at a space-time, the energy density would then decide the curvature of the space-time by Einstein's equation. So the fluctuations in the energy density would also lead to fluctuations in the curvature of the space-time. And those are the fluctuations which all the particles would get. Let's assume we have another field, some spectator field, which is just residing there and watching inflation go. That field will also get some fluctuations, and those fluctuations are adiabatic, but it can also get its own fluctuation, some homogeneous fluctuation. And those fluctuations here are the non-adiabatic fluctuation. And this is the quantity that we essentially call as adiabatic fluctuation. Sorry, isocurvature fluctuation. So it's like looking at, I have a harmonic oscillator. That harmonic oscillator can be source driven. You have an external source which drives it. And in that case, that external source driven fluctuation or the oscillations would be just driven by this field. And that's what we call as the adiabatic fluctuation. But apart from that, that harmonic oscillator can also have homogeneous oscillations. And those homogeneous oscillations do not depend upon any external source. They are standalone solution for that harmonic oscillator. And that's what we call as the isocurvature fluctuations here. Now let's see what exactly we mean by the power spectrum for these. Okay. So what I was trying to say through an analogy is that if I have a harmonic oscillator, and if that harmonic oscillator undergoes its own oscillations, those are harmonic oscillations. Now one can also, and that harmonic oscillation will depend upon the mass of the harmonic oscillator. But on the other hand, I can also drive it externally through some external source. So the harmonic oscillations, the homogeneous oscillations without an external source, are similar to isocurvature, but anything externally driven, and in case of inflation, the external driven is actually a lot because we see almost all fluids have adiabatic. That external driven source is the adiabatic fluctuation. So you have n number of oscillators, all of them are externally source driven, all of them will oscillate exactly similarly. That is the adiabatic solution, but they have tiny differences between them. That is their individual homogeneous oscillations that they have. So this is just an analogy to understand isocurvature and adiabatic. Now, what exactly is power spectrum in that case? So I'm looking at quantum fluctuations, We see fluctuations today in matter density in terms of stars and galaxies at different scales. Galaxies are kiloparsecs, and clusters of galaxies are megaparsec. And at each scale, I can measure how much inhomogeneity I see in the universe, in the spread of the matter as such. But how do I measure these and how do I quantify them? And so statistically speaking, I can do so in terms of defining of, so these are fluctuations, right? So these are supposed to be random fluctuations. And assuming that these fluctuations are Gaussian, I would say that these fluctuations have something like a Gaussian spread around 0. And so by taking a mean, you don't really get anything because these are random fluctuations. They may have some amplitude here and some amplitude here, but they also have equal amount of negative amplitude. So eventually the mean is just 0. On the other hand, what we are rather interested in is that any fluctuation will have a specific variance. And that's the thing which we measure. And in cosmology, we call that variance as the power spectrum. And this analogy, again, comes from the networking part, I mean, the network physics, actually. So the idea is, given any PDF function, if it is Gaussian, then its mean is 0. But then we can measure what its variance is. And this variance essentially is the one which we call power spectrum. Now, what exactly is K here? The K is at different length scales. So this is a wave number, and this is 2 pi over L. So at different lengths, I'm trying to measure how much is the variance of this fluctuation. And instead of saying in terms of L, we write in terms of wave number. Because Fourier analysis, things become linear, they become decoupled, and it's easier to study them. So just to give an idea, if I have a Gaussian PDF probability distribution function of some perturbations, this one has a small variance and the blue has a small variance, orange has a large variance. So clearly for any fluctuation that I have, so this is fluctuation which can be positive or negative, this fluctuation, there is more probability of that fluctuation occurring in orange than in blue, purely from the logic of a probability distribution function. So larger the variance, the more we say there is a probability of that fluctuation to occur. Now, once we have defined what this power spectrum is, which is just the, sorry? No, it's not shifted, it's at 0. This line, I was just trying to show for a fluctuation of value 1, how much power this has versus how much power this has. And that's purely dependent upon the variance of them, if I have normalized it correctly. Now, having defined a power spectrum, we still need to go one step ahead before we go to the final parts. And that's, I'm going to define something like a dimensionless power spectrum. So I multiply that variance or power spectrum by a volume factor. This K cube is just a volume factor in Fourier space to make things to normalize the power spectrum, essentially. And then the final value is written in terms of this parametrization. I have some amplitude of the variance. And then I'm trying to see, is there a K dependence? Is there a scale dependence on my power? Is the power at large scales much different from the power at very small scales? So how do I quantify that? And we quantify that in terms of this function. So this is one such way of quantifying. It's called a power law quantification. And the idea is this A is just the amplitude of the fluctuation, which is common for all the scales. Then we have the scaling. Kp is just some fictitious or a pivot scale that we choose, and we fix that number. And then we look at different values of K. Remember, small k implies large length scales, and large k implies very small length scales. This n is called the spectral index. And if n is 1, then there is no scale dependence. It's just flat. All scales have equal power. But if n is greater than 1, you get a tilt, which goes up. And if n is less than 1, and you get a tilt, which goes down. So that's what we call blue if it is greater than 1. And that's where the definition of blue comes from. So if n is greater than 1, the power spectrum increases, something like this. So this is the primordial power spectrum. And from the best, so from our measurements of CMB and also from the measurements of galaxies that, in fact, clusters of galaxies that we have today, we know that the primordial fluctuations had an amplitude about 10 to minus 9, and they are almost flat. So all the scales at all length scales, whether it's the length scale of a galaxy versus the length scale of a cluster of galaxy, or whether the length scale of a star, the power of fluctuation or the variance of that fluctuation is almost the same. Now, one caveat here, this is primordial. This is at the beginning of inflation, somewhere before radiation dominated era. Because today we know we don't see the same thing. We know stars and galaxies have clustered together. So there is huge variance and huge power there versus the power on a very large scale. So this is what we are looking at primordially. So what it was, essentially we are trying to write the history. We are trying to go back in the time and then try to see whether we can measure this power. And so this is adiabatic. We know from the measurements that the most of those fluctuations had to have been adiabatic, implying they are directly coming from inflation. And if there was any isocurvature, it's extremely small, 2% or less. We haven't really been able to zero it down, what is the percentage of this, but it's about 2% or so. And we would expect isocurvatures to exist, especially if we have dark matter particles. Now, as I said, these are flat. There's nothing, if all of the isocurvature is just flat and if it is 2%, there's nothing interesting. On the other hand, one can have isocurvature, which is blue. In this case, it's blue tilted, so it's going up. Just to remind, this is K. So again, this, if you take inverse of this, that just becomes the length scales. So this is the length scale where galaxies are, and this is the length scale where clusters of galaxies are. And so I'm saying that I can have a situation where the isocurvature power just increases. So there's more power along very, very small scales and less power on large scales. On the other hand, I can have a situation where it goes and then cuts off. That's also, in fact, this is a more natural circumstances from an inflationary point of view. And I'll try to explain why. Uh, right, so these are some bounds from the currently known measurements. We have from CMB, we know that the isocurvature should be 2% or so on all the scales less than this value, which is why we have about 2% here for isocurvature. Now I can always fulfill that 2% by instead saying, okay, my isocurvature power is not flat, but something which is blue. So it is naturally very small on these scales. But if I were to tomorrow do a measurement on these scales, which we are still trying to probe, I will actually see a large power from isocurvature. Is that clear? So right now, we only have measurements from this region. We do not have good measurements in this region. And what my measurements from this region say is that the isocurvature, the green part, should only be 2%. But nothing stops me from saying that instead of this flat, the isocurvature is actually tilted like blue or orange, and which is why it is very small where we have measurements. And so on very small scales where future measurements are going to probe, I can actually get very large power. And that's where things will become exciting. Okay, yeah, we can skip this. Now, why are we interested in blue isocurvature? Even if tomorrow I see a blue tilted isocurvature from very small scales. So suppose I'm able to actually uh, I'm able to probe this region and I suddenly see, and I'm able to measure this blue power, which goes over the dead adiabatic. And what does it tell me essentially? Now, the isocurvature, blue tilted isocurvature, one of the sources of blue tilted isocurvature is during inflation. And so it gives us a peep into the inflationary era. And actually the tilt, or this tilt that we see, this tilt is just an arbitrary tilt that I have added. The slope can be anything. And the slope actually gives me an information about the mass of the particle that was carrying the isocurvature fluctuation. And this is something which is very unique and interesting. So as I said, the tilt actually gives me an information on the mass of the spectator field or the field which was there along with inflation. Now, during inflation, you can have very light fields. You can also have very massive fields. And light fields would not give me anything interesting from the point of view of fluctuations, but massive fields actually give rise to such sloped power spectrum, and which means there is large power on small scales, so I can get information about those. And in fact, there is one can also have bumps and oscillations on the isocurvature power spectrum, which means I can have a situation where there are bumps on this and oscillations on this. And those oscillations and bumps, again, give me an information about the fields which were oscillating at that point of time. And again, this gives me an information because those are harmonic oscillations and they're directly related to the mass of the field which was oscillating. So once again, I can know an information about what was the mass of the particles or the fields which were residing during inflation. And yes, JWST has recently seen several early galaxies, something which defined the current cosmological lambda CDM. We are really struggling to explain why do we see such early galaxies, galaxies that should not have existed from our current theories. And one explanation for them is that if I have such large power, then it is very, very possible to form galaxies very early, just because I have a large power. And that means I can explain the JWST measurements. It's again an ongoing work. People are still trying to do calculations to see if this works. Exactly. I can still have a situation where I have a power which increases adiabatically here. And then that would imply that one will have to change the theory of inflation slightly, have some features in inflation, maybe ultra slow roll, or have a small kink or a bump in the inflationary sector. Again, it's possible. In this case, when I say field, I have the inflationary field called the inflaton, which is actually causing the inflation. But then apart from that, we are looking at the dark matter field. And the reason being, even though there are n number of fields that can exist along with inflaton during inflation, they will carry isocurvature individually. It's not probable that all of those isocurvatures will survive today. Isocurvatures suffer from something called an annihilation, and only very special isocurvatures will survive. And by special, I mean they have to be carried by something which is very, very weakly interacting. And that one situation for that is called dark matter. A dark matter would not really interact. So any fluctuation that it has would be surviving today. And so this is also one of the reasons why, even though there was maybe some large isocurvature, probably that did not survive today, and which is why we don't see it. Yeah, I'm talking about the isocurvature in the dark matter field. So we have the baryons that we know in terms of the light which is emitted, but we do know that the mass of the universe, the total matter that we see is not just made of baryons. There is some extra matter, something which we haven't been able to account for. And the only way we can account for is by introducing something called a dark matter. And it is that dark matter because it's not interacting electromagnetically. The only way it interacts, it's gravitationally. And because it's not interacting with any other photons or the baryons directly, any fluctuations in it will remain conserved. They don't get washed out. And so there's a whole program. People are still trying to find out dark matter particles. But from our best theory, we believe that it's going to be a particle, and it does exist. The other logical thing would be to modify gravity, modify Einstein's gravity, which has very little support right now. Uh-huh. Mm. Yeah, right. So the fluctuations for the light field would be scale invariant. Exactly. And they would just be flat right here. And if they are, because they are any other field, they will also have isocurvature, and those will be simply flat. And we know flat isocurvature is only 2%. So even in future, at very small scales, they'll just remain 2%, so nothing interesting. But if it is a heavy scalar field, then its fluctuations will be blue tilted. And in that sense, there is an opportunity to see them in future. And as I was saying, isocurvature perturbations can be easily attenuated. You can easily wash them out. And the problem being, you can have fields. So these fields, if they carry isocurvature, let's say the dark matter field carries these fluctuations isocurvature, they can interact with baryons gravitationally or somehow, and then lose all that isocurvature. Or you can have a field which carries isocurvature, but then it decays. Again, you get rid of the isocurvature. So you need to preserve isocurvature in order for us to see today. And the most easy thing for that is to assume that it's a dark matter particle, so that the dark matter particle, because we know it's very weakly interacting, the fluctuations in it will not get washed out and will remain preserved for us to observe today. And one such dark matter particle is axions. And so I'll be talking about axions. Axions are well motivated, in fact, from both particle physics. They were, in fact, motivated from particle physics perspective, and soon cosmologists lapped up onto it, because this is an amazing particle in terms of, there's a whole, I'll say, subfield in cosmology, axionic cosmology. So axions was initially, just to give a brief overview, they were initially proposed as a solution to the strong CP problem, which is a problem with the lack of a CP violation in the QCD sector, particle physics. And then Peccei and Quinn, the two scientists, they came up with this solution, nice solution. And Weinberg later and Wilczek, they found that their solution actually admits a new particle, which is called the axion. And then because that axion is very, very weakly interacting, cosmologists liked it. So they said, okay, now it can be a dark matter particle. And so there's a whole field behind axions. No, there are several experiments people are trying to detect. I think one of the most sought after dark matter particles. It's probably gone above and beyond BIMs at this point in terms of such. Right. So how do I generate? So I have been talking. Yeah. Mm-hmm. 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 Yes. In addition to that, you have one more species, and that is your cold dark matter species, the axion. Yeah. Rather than thinking it in terms of particles, they're saying that there's a field of axion. Exactly. Mm-hmm. Photons. Right. Exactly. And I can also say, instead of talking in terms of fields, one can also talk isocurvatures in terms of the fluctuation in the number density of axions. So if I take axions as just particles or dark matter particles, and if I'm talking about fluctuations, so what fluctuations? There it would be the fluctuations in the number density of the axions. So there is a uniform number density, but then in some places axions can be more and some places less. And that fluctuation in number density comes to be what the isocurvature is. So isocurvature is kind of a fluctuation. It can be fluctuation in the energy density or fluctuation in the number density. It's about which gauge you want to study it in. Mm-hmm. 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 Yes. At least that part will be exactly adiabatic. Mm-hmm. Mm-hmm. That would be isocurvature, right? And which is why it's extremely small, because all the fields, if they interacted together, they would have almost the same fluctuation, which is the adiabatic fluctuation. So as I was saying, how do I generate a blue? I have already said that one can have a blue tilted isocurvature where the slope is increasing, but how do I get that essentially from particle physics? And this is where some of the particle physics would enter. And the idea is so I'm going to take the most basic form, and this is where you have a complex scalar field. This field can be factorized in this form where you have one field that is the radial field. And then I have this theta where I write theta in terms of A over R. This A is called an axial field. So I have a complex field which has real parts and imaginary parts. But instead of writing it in terms of a real field and an imaginary field, I'm writing in terms of a radial field and an axial field. It's just a different kind of parametrization. Now the idea is that the fluctuations in A, which is what we will define as axions for now, divided by whatever is the background value or the static value, is what we get effectively as the isocurvature fluctuations. And this power spectrum, this here is just the shape of the potential. I'll come back to why the shape of the potential looks like this. So how do I get a blue tilted isocurvature? The idea is the variance or the power. As I said, the power is just the variance that we see, and which is also defined in terms of these are just same exactly. Is coming back to, sorry. Mm-hmm. No. Inflaton is a completely different field here. So this phi field is the Peccei-Quinn field and just a spectator field. And the fluctuations, you will have fluctuations both in R and A. The fluctuations in R, because R is heavy, it will eventually decay, will not survive. A being light and being the axion dark matter that we call today will survive. And so we are interested in fluctuations of A. So right now we are trying to study how do I get the fluctuation that I've been talking about. I've been talking about blue tilt, that slope, but how do I generate that tilt from an inflationary physics perspective? And so the idea is during inflation, I can have this field phi, which is actually a combination of two fields, real or imaginary, or in this case, radial or axial. And then the axial is what we call as the axion field. We identify the axial as the axion field. Oh, right. So okay, so this is the isocurvature quantity. So through some mathematics, we actually get that this is the isocurvature quantity. The fluctuations in A divided by, so this is a relative fluctuation. I have the A, which is axion field. It has a specific amplitude, but the fluctuations in them is delta A. And it's the relative fraction between this quantity that is called the isocurvature quantity here. Now, the fluctuations in A actually are directly related to the Hubble scale or the energy scale during inflation. So H is some kind of an energy scale during inflation. And so the idea is the energy scale sets some kind of a temperature. And just by going to the kinetic theory, if I know the temperature of of a gas in a fluid, of a gas in a box, and I can actually know the kinetic energy of the gas or the molecules just because I know the temperature. This is macroscopic. So going from macroscopic to the microscopic, I know the macroscopic temperature, and then I can get some idea about the mean fluctuation of the velocity. So these fluctuations are then directly related to this H, which gives me the energy scale during inflation. INF stands for inflation here. And A, by virtue of this expression here, theta is equal to A over R. So A would be R times theta. And instead of writing just R, I'm saying R is a specific value, which is FA, just giving it a specific value. I'm not going to explain why it's called FA, but for now, it is this value FA that we specifically choose. Because this value of FA comes again when we actually study axions later on. So it can be, right. Now, how do I generate a blue tilt? The idea is, as I said, this A is nothing but R times theta. Now, instead of saying R is constant at FA, what if R changes during inflation? So if R changes during inflation, then I can actually generate fluctuations that are also changing during inflation. And so the idea is this R, which resides here, this is my potential. Maybe I can draw it here. So I'm just drawing the radial part of the potential. And so this is radial amplitude, this is 0. Assume that the potential field is actually sitting here and it's trying to roll down. So it goes from a large value of R to a value of R, it will eventually sit here. So if the velocity is not much, it will eventually come and sit here. This is what we call as FA or FPQ. But if it starts from here and if it's rolled down, the denominator here goes from a very large number to a very small number. Now, when it is large, the values are small, and then it eventually keeps increasing because R becomes small and small, R becomes small. And when R goes to FA, it just becomes constant because R sits at FA. So this is how we generate in one way a blue tilted isocurvature. You start with a radial field which is displaced, let it roll down. During rolling, it generates this blue tilt. And then once it settles at either this or this, those minima, it just becomes flat because nothing is changing after that. Right. So we will have to look at different models for displacement. And the most celebrated model, I would say, is before I come back to your question, right. So this is what one would get. So as, oh, okay, sure.
Value of R is order n plus, is that what?
Less than m plan, not exactly m plan, because um, we already have super radiance limit about 10 per 9 GeV. I would say greater than that. There's no specific limit. The value of FPQ, see, the rolling only depends from where it starts to where it's ends. Depending upon where it starts from to where it ends, that defines how long it's going to roll. And different models for different values of FPQ, or for different points where it starts from, I can get different scale over which it grows. So this part of the spectrum where the whole thing is growing, that can actually span across several length scales. So it depends what length, how many length scales do I want? Do I want to go from the size of superclusters of galaxies to a galaxy scale, or do I want to go from superclusters to scale of a planet? And that scale then determines how much my M be, I mean, where it starts from to where it ends. And I think the most direct information about this would rather be obtained from the plateau, because this is purely H over FPQ. And assuming that my theta is order 1, so this is roughly this. Again, it gives me a ratio of H over FPQ, not exactly FPQ. But then I can get H from gravitational wave measurement, primordial gravitational wave. So there are different ways in which I can get. And I can also get value of FPQ from terrestrial experiments, which directly probe axions.
Fine with the large values of it.
Is fine, yeah. No, not 10 power 15. I think if I start from 10 power 15, which is close to the string axiverse, then this is already 10 power 17 something. There's hardly anything left for me to roll. From 17 to 15, it goes very fast. I won't be able to generate a large range. I need a large range at least to explain the current observations. So I would say FPQ should be uh, about 10 per 11 or 12, but not more than that, to allow for a large range. Otherwise, I'll have to slow it down even more. And I can slow it down by saying that the mass of my PQ field is extremely small, but then it also makes this tilt go away. It makes it almost flat. So there's not much wiggle room, in fact. Mhm. Okay.
Not directly rolling down, but maybe first going the other way and then coming, and then you can have a.
Oh, yeah, yeah. Yeah. But
You can have,
mhm, mhm.
you can have a range of
Mm, sort of. If I can have a model where it first rolls up, then clearly during the time when it is going up, you would have probably a red tilted, in fact. So it would go this way, and then again it would go the other way. Uh, um, it will roll during inflation. So the idea is sometime during inflation it begins rolling. How do I define that sometime is free to how many scales, because this range, and I can place it anywhere within the observations. All I need to make sure is that the amplitude should be below what the current constraints tell me. That's the only restriction on it. There's no other restriction. And of course, tomorrow, if I measure some amplitude, then that would actually set a scale for me straight away. And this is just two different plots that I was showing. Mhm.
saying that when it rolls like that, this is the
Mhm.
this is basically a more detailed version of just this, right?
Exactly, exactly. Yeah. This is from numerical runs. And the small bump we see is because the field just can just doesn't roll and sit here. It goes slightly up and then comes back. And if it has too much power, it can actually go up and then keep oscillating here. And if it keeps oscillating here, you get more bumps. This already shows that there is another bump. Yeah, lots of biggers. And that can be complementary to the cosmological collider signals that we have. In fact, we are working on a small project where we are trying to see if the BO oscillations, so the BO oscillations do undergo some kind of an IR effect where they become smaller and smaller. Now, there is, people have already seen some oscillations in Planck at the beginning of the BO oscillation, whether that can be explained through this. It's again, very speculative from that point of view. Sorry, I forgot your question. Uh, oh, how does it get stuck, right? Yeah, so this is a very generic PQ model. And again, I'm going to replace R and A with gamma and sigma, just because A is going to become my scale factor and I don't want to confuse anyone. And instead of R being a curvature sometimes, so I'm just going to say gamma and sigma. So just reminding everyone, radial field is gamma and axial field is sigma. This is the most usual potential, PQ baking potential. And in this case, we assume R is initially displaced from Wave. And one such, how do I displace this? And one idea is you can have it trapped there and then to any other field. And then when that field relaxes, the trap goes away. And so the field comes down. But Kasuya and Kawasaki in the celebrated model said, you don't need a trap. You can come up with other mechanisms as well. So the first question is, how do I slow down this roll? Because if this curvature, which is given by this part, is extremely large, it will just roll down very fast. And as I said, I need sufficient amount of scales all the way from clusters of galaxies to the galaxy scale. That's enough, very large scale actually, from hundreds of megaparsecs to kiloparsec, about 1,000 factor. How do I get that here? Because remember, the blue tilt exists only as long as it is rolling. Once it stops rolling, there is no blue tilt. So how do I ensure that it rolls slowly enough, but not very fast? So the Kazuya Kawasaki came up with this model. This is a SUSY-emitted model, actually. Uh, so I'm not going to spend much time, but this is going to be highly technical. The more interesting part of this is that the potential looks like this. You have two fields in this is so in fact we have three fields, three chiral superfields. Let's just say instead of one PQ field phi that we saw initially, I have two PQ fields. And now these two PQ fields are interacting in such a way that the total potential looks like this. It's not a one-dimensional potential, but rather two-dimensional in two radial fields. And both have some mass term. And then there is also this term. It looks like a quartic potential, but note that I can always choose phi plus and phi minus such that this part is 0. And in that actually means that there is what we call a flat direction in this. So I have a flat direction essentially. So if I were to draw phi plus and then phi minus, this direction, phi plus can be extremely large, and then phi minus can be extremely small, and it can still satisfy FA square so that the whole quantity just vanishes. So I can go from this to this along this line, and nothing changes in the potential. So it's like an equipotential surface, but in our sense, we say it's a flat direction line. And so I can easily roll phi plus to extremely large value or large displacement without actually doing anything with the potential. So that's the Kasu and Kawasaki's way of ensuring a large displacement. I hope that answers your question. Yeah, mass term will get affected. And so this mass term, if I tune initially C plus such that it stays and it rolls only slowly and effectively C plus becomes large. And so there is also a trap which can exist. So the most important aspect is there is a quartic term, but that quartic term doesn't really play any role. So all the rolling takes place only along a quadratic potential. And because quadratic potentials have this nice mass, which is almost constant, so the curvature remains exactly the same. Whether it starts from Planck scale or all the way to FPQ, the curvature is never changing. So I can always carefully tune the curvature to make sure that it rolls for sufficient amount of time. But downside of it, you get rid of the quartic term. There is no quartic term in this. On the other hand, most generic PQ models actually have this gamma 4 potential term. So our question was, is there a way to generate without having a flat direction and just with a single field instead of two fields? Can I do this with just a single field with a large displacement and with a quartic self-interaction term? And so this was kind of a motivation for us. How do I generate the blue isocurvature? Very, very different from what Kasu and Kawasaki do. So Kasu and Kawasaki require two fields, they require a flat direction, and they require several things in order for this to work. But that is not the generic model. The most generic celebrated model is rather, I would say, this. So how do I generate blue isocurvature here? And the answer actually exists very much in the literature, but from a completely different perspective. And when we started this project, we were trying to look at something else, and we just stumbled upon. So we were trying to look at some rotations in from other perspective. We were looking at Lorentz breaking, Lorentz symmetry breaking, and then we were looking at some superfluids just for fun. And then we thought, oh, we can actually apply it to the isocurvature models. And so the idea is, yes, I can actually slow roll, even in the case where there is a gamma 4, if instead of going straight away down, it spirals down. And that is, instead of going straight away down, let it spiral down. And the spiraling ensures that it doesn't straight away go down. It actually takes huge amount of time to come down. And this spirals actually implies that there is a PQ charge, there is some theta velocity or the velocity along the angular direction. And that angular direction actually is a conserved angular momentum in this case. So once I generate that kick, if I give it an initial kick in this direction, that kick will ensure that it doesn't roll down, but in fact, it goes round and round. And that kick is very easily accomplished from an Affleck-Dehn mechanism, in fact. And interestingly, this ensures that in almost all, this directly gives a very generic result. It results in the mass being 2h square, no ambiguity there, and it essentially gives Ni equal to 3. So the spectral index is fixed at 3. Once you give it a kick in the angular direction and make it go in a spiral motion instead of coming down, the spectral index is definitely 3. It doesn't change. The wiggle room to change away from 3 is very less. And there's a reason for that, because the gamma 4 potential actually is a conformal potential from a cosmological perspective. It's a conformal potential. It has this conformal symmetry. So I'll have the a power 4 factor, and then with gamma power 4, that a power 4 and gamma 4, as I will show, gets absorbed. And that essentially leads to this kind of a scaling where this is just 3, Ni3. This is the effective mass of the roll down. So I can have, so essentially if m square is extremely small, so initially the potential here is just given by negative m square, and this is my gamma to the power 4 part. And if it is somewhere here, it's not actually seeing this, but the effective mass is lambda gamma square. On the other hand, if it is rolling, even if it is here and if it is going in a spiral motion, the mass is not lambda gamma square, but rather it is directly 2h square. There is no ambiguity on this. This is because it's purely defined by the conformal symmetry that comes to play when you have this kind of a spiral motion. Yeah, any questions on that? So maybe I'll try to explain this in using, so we have this potential, as I said, there is lambda gamma 4. I think it should be 4 here. Yeah, lambda gamma 4, sorry. So this is the lambda gamma 4 in log scales. I have gamma, and this potential just goes gamma to the power 4. Now, because I have what we call an angular motion implies an angular velocity, that angular velocity gives rise to a term like this, which in terms of the angular momentum, which is conserved, I can write it this way. And that actually implies that there is another part of the potential which is going this. So in fact, my field is stabilized at this point due to the presence of angular momentum. So the angular momentum acts something like a centrifugal force. So it avoids the whole thing from falling radially inwards. And that centrifugal force makes sure that it is stable in an orbit. And in fact, if there was no expansion during inflation, this would just be a stable orbit. Any questions? Yes. Or in fact, it can have a radial velocity, but in the situation where you require, so if I have a very large displacement, that large displacement also requires an equally large cake. And in those cases, even if there is a radial displacement, that radial displacement would cause an elliptical motion. And I'll come back to it, the presence of an elliptical motion. So instead of going pure spiral, it can have slightly ellipse, and that can cause parametric resonance. Yeah, so that will cause parametric resonance, and it will actually destroy all the isocurvature. So there is a nice window within which you can have this situation, and beyond which you will just destroy the isocurvature. In fact, you will generate lots and lots of axionic particles from that parametric resonance. Now, the next part is going to be even more technical beyond this. So we start with the most. So what I'm going to show next is how do I do this? So this was just an explanation from a background physics point of view. Now I have to look at the fluctuations. So I have to actually derive these fluctuations. And the problem is because you have this situation where the radial field is spiraling down, it is spiraling and also coming down. This actually implies that the axial field and the radial field are very strongly coupled with each other. And due to this coupling, there is no consistent quantization. You need to quantize the fields before you can study the power spectrum for the fields. And from a inflationary physics point of view, this quantization is very essential. And we then decided to look at the quantization in this situation where there is very strong coupling between the two fields, the two fields being radial field and the axial field. So we have the most basic action. I have my metric determinant here, and I have a complex scalar field, and then the potential. This is the quadratic part with a negative, and this is the quartic part, the potential. Mm-hmm. In the axial field, Yes, yes, yes. Right. So because they are coupled, we. Mm-hmm. Yeah, it actually bleeds onto the axial part. Even if there are fluctuations in radial field, those will start affecting the axial field, and the axial will start affecting. So in fact, we found through the quantization there is no orthogonal state here. Even though we get two eigenstates, one eigenstate is light, which is the Goldstone mode, another which is heavy, they are strongly coupled. So there are two modes, but they are very strongly coupled. And due to that coupling, they're not orthogonal, unlike the usual states. So we have a gapped state, in fact. So something like this. We have a situation where as k goes, the Goldstone mode goes this way as k. In fact, k over √3, and this is the other state which goes this way. So there is a gap here. So this is the light state, and this is the heavy state, two eigenstates. It does, in fact. So every right. So what happens every time the radial field rolls, the axial field gets a mass. So the mass of the axial field essentially is in a PQ Due to the PQ symmetry, it is supposed to be cold stone, so it's not supposed to have any mass. But because the radial field is moving, the dynamics of the radial field, the time-dependent dynamics of the radial field gives rise to a mass to the axial field. And that's what decides my slope of the isocurvature fluctuation for the axial field. And all of that is automatically embedded in the full calculations that one does, and we still see a spiral motion. So the spiral motion will eventually end when it comes to the bottom somewhere here. No, no, no. It's the mass which is generated. Yes, yes. It's generated through Hubble interaction. So without any Hubble interaction, it would just be if there was no Hubble expansion and if there was sufficient kick, then the radial field would just be going round and round, just like a satellite and not never come down. But because you have an expansion of the universe, it eventually loses energy and then it has to come down slowly. And this occurs through a very special conformal symmetry, making sure that this rolling down occurs only as 1 over A. It doesn't roll down faster than that. And this 1 over A effectively gives rise to the 2h square through the calculations. Mm-hmm.
And that usually also you will have, even if you don't have any of this motion in the field space, usually you will have a potential generated for the axial field, right? That
if there is no motion, if there is no radial motion, because if it is, yeah. Oh, this is during inflation. This is during inflation when the axion is massless. So we still do not have the QCD potential come up. So the QCD potential will come much, much later. In fact, right now, there is, yes, exactly. It's just a flat direction. But it gets a mass purely because the radial field is moving. So if the radial field was not moving, we would get a massless axion. And that gives a very generic scale invariant isocurvature. That is not what we are interested in. We are interested in blue. So how do I get blue? I make radial field move. And because radial field is moving and it is coupled to axial field, it will lead to the generation of a mass for the axial field. I think I'll quickly wind up from here. The basic idea is I can always redefine the gamma fields. This is complex scalar, theta well field, and then the radial field. I define a new field y where I multiply the gamma field radial field with A. And the idea is once I do that, I rewrite my entire action, which has, so this essentially gives me direct information of the expansion of space-time. Because this is FRW metric, it has this A to the power 4. And that gives me an information that we are sitting in a de Sitter space-time, which is expanding. But now, this has no information. So this is just a Minkowski metric. And the Y field essentially sits in if I neglect these terms for now, the Y field has no information that it is sitting in an expanding space-time. So the fluctuations of Y will also be just Minkowskian. The only way it gets information about expansion of space-time is through this term, which actually breaks the conformal symmetry, and this, which breaks time translation symmetry. So these are the two terms. But if I have a large displacement, then these two terms are just negligible. So I make sure that my displacement is so large that I can neglect these two terms. And then my new theory has these two terms and this, and there is no information of A square anywhere in this in terms of the Y field. So the Y field as such assumes that it is just sitting in a Minkowskian metric. It doesn't know anything about space-time. Even though the space-time background is expanding, this field thinks it's sitting exactly in Minkowski, which makes sure that the fluctuations are frozen throughout the time. So even though it is, now I'm going to use technical words, even though it's sub-horizon, the field remains frozen. Unlike the situation where fields remain, the amplitude becomes frozen only super horizon. In this case, even sub-horizon fields amplitudes are frozen. And yeah, this is just to show that even with this kind of a situation, I can just show that in order for the Y field to be exactly constant, I just need to make sure that the theta square cancels with the Y4, which gives me this kind. So the cancellation between these two terms, this is the centrifugal term and this is the radial force term, or the radial potential and centrifugal potential, implies that my amplitude is set. This is similar to circular dynamics. So there is the radial potential gamma 4 making it go down. And then there is also a centrifugal force purely because of this angular motion. And there is a stabilization between these two, and then it undergoes a spiral motion along a certain radius. And the radius eventually has to go down because of the expansion of the universe. and because the energy dilutes. So just to say that if initially I had if there were no rotation and if there was gamma 4 potential, the radial field would quickly drop down from a very large amplitude in very small number of e-folds. But now because of rotations, it actually goes very slow as a factor of 1/a. So the amplitude reduces very slow. And this is to explain, if there is a radial velocity, instead of just going as 1/a, there are small oscillations. This is the elliptical oscillation that we are talking about. And these oscillations can become large, depending upon how large my radial velocities is. And if this becomes very large, then this directly becomes a source of a parametric oscillation for my axial field. So you actually get parametric resonance. That was all about radial sector, but in the axionic sector, the things are interesting. Again, I can start with this. Because here there is no other part other than theta theta, which talks about axions. Axions live in theta theta, so this is the only part that I can write. And then if y naught, which is y is a constant, I can always take them inside. And I can define my axion field as y times theta. Now, this field, I rewrite it here, is again Minkowskian, has no information of an expanding spacetime. And this term here is just in mixing between y and a, between the radial field and the axial field. And in fact, that mixing is related to theta dot. And because theta dot is extremely large, it's a very strong mixing. So what it does, it changes the dispersion relation for the Goldstone mode. So instead of the usual k square that we say is the Goldstone mode, it is not k square, but k square over 3. So the speed of sound for the dispersion relation for the Goldstone mode changes. I think we are approaching time. Yeah, okay, I'll just finish. So the main idea was you go from a situation where initially y is almost a constant. So you live in the axion field lives in a time-independent conformal phase. And then as soon as y reaches, because the y field radial field has to eventually reach the bottom. As soon as it reaches the bottom, the shape of the action changes into this. And now all of a sudden you see this time translation breaking term. So the axion field initially doesn't know anything about background space-time. And suddenly as R reaches here, the axion field suddenly sees this term. So now it knows it's living in a background space-time, expanding space-time, and all the modes exit instantly, although they are frozen for the entire period of time. So this is a near spontaneous, I would say, breaking of time independent to a time dependent phase that's happening. Plus, there is, although this is just the talk about these terms, there is also a very strong radial and axial coupling because of this theta dot, which changes the dispersion relation. And what we did, because of this strong coupling, you need to quantize the field in a very careful manner. So we did some quantization of it, starting from explicit quantization. I'm not going to go into details. The difference is you have two eigenmodes. They are not orthogonal. One gives you a light eigenmode, another gives you a heavy eigenmode. And the fluctuations that we really care about are just given by the lighter eigenmode. These are the ones which will survive. This one doesn't survive. So it's like saying the axion field is supposed to get just one mode of fluctuation, but because it is coupled with radial field, together they will have two fluctuations, two solutions that they will share. One solution is the light solution, another corresponds to a heavy solution, and both the fields have both the fluctuations in this case. And only the light one is the one we really care about, this one. And by k square over 3, I'm sure you will recognize this looks like if not for the 3, omega square equal to k square is just like a massless particle. But the 1 over 3 is coming from the dispersion relation being changed due to the strong coupling between the two fields. Now question can be, the k square just gives me a k square tilt for the power spectrum. The power spectrum has a blue tilt. But can I measure this 1 over 3 in future? And actually, so this is how the power spectrum looks like. These are different contributions. This is the heavy contribution, which is very small. And this is the light contribution, the green. And the red is the sum of light, blue, and green. Green is light mode, and blue is the heavy mode. In fact, that 1 over 3 directly comes in. So this is where you have epsilon L, and epsilon L is just the radial part. The radial part, if it has some small radial velocity, or if it has some small disturbances from the spiral motion. And these are exactly embedded in the form of 1 over 3. So this is actually cos of k over 3. So the 1/3 dispersion relation also shows in the form of the oscillation on the blue part of the spectrum. So the spectrum not only gives me an information about the tilt, so the tilt is exactly k square, but the oscillations on top of the tilt also give me information about the dispersion relation. And this is just the last part. So we tried to do some calculations and see this in the data. So we used EFT of LSS. So essentially we looked at galaxy data. So in the galaxy data, can I get some measurement of isocurvature? Euclid is already up there. MegaMapper is replaced by Spec 5. And this is going to be the very futuristic 2030 probably. And this was done with Moritz Manchmer. And we found something like that. This is the current Planck constraint on the amplitude. So alpha is the ratio of isocurvature amplitude to adiabatic. And this is extreme. This is right about here. And Euclid would go about a factor of a few, but MegaMapper can actually do much, much better. MegaMapper can give a factor of 10. But this is just a forecasting to see what is the possibility of detecting these in the future and how good the current or the future experiments can actually probe. Yes, alpha is the y-axis. And this is the slope. Depending upon the slope, the larger the slope, the more is the sensitivity for measuring these isocurvatures. Right, and that's it. So this is just a short summary. So we have, as I said, it's a near spontaneously theory which flows from a time independent to a time dependent, and it gets that near spontaneousness only when the radial field settles exactly at the bottom. The isocurvature is frozen even during subhorizon. Because of this, there is a strong correlation, and actually this strong correlation gives rise to nice interesting non-Gaussianity. And yeah, the dispersion relation is slightly different. Instead of k square, it's k square over 3. And it gives me a k square isocurvature spectrum. So it mimics a flat direction without actually having a flat direction. Thanks.
We talk about, let's say, usual adiabatic perturbation. So for curvature perturbation, we'll impose these Bunch-Davis initial conditions, right? So if you don't impose them, then the power spectrum is very different.
We are still imposing some sort of Bunch-Davis, but
this case, that is applicable because
good question. It's not directly applicable because there is a strong coupling between the two fields, which is why we have to do the explicit quantization. If they were not coupled, then I can directly apply the Bunch-Davis solution and Bunch-Davis vacuum and then do all the calculation, in which case I'll just get k square is equal to omega square or omega is equal to k dispersion relation. But because there is a strong coupling between the two fields, there is a natural, one would have to entangle this and actually look at the two diverse eigenmodes, and only those eigenmodes should be applied with the Bunch-Davis should be applied to only them. And that's what we did. And in that case, when we do that, we get one is a heavy and another is a light. And we consistently apply Bunch-Davis to the heavy and the light. So in fact, it's like the two fields coupled together to form two different directions. And those two directions actually have Bunch-Davis solution. But because of the coupling, it's not orthogonal. There is not much choice, I would say. Of course, one can change Bunch-Davis to an alpha vacuum situation, and that would definitely give rise to. But I think going at the lowest energy, if I just want to apply a ground state or a Bunch-Davis solution, then I have no choice. I can, of course, apply excited state solutions.